Hybridization is the linear combination of atomic orbitals in an atom. Typically, carbon, nitrogen, and oxygen hybridize their s and p orbitals to form bonds. An isolated carbon atom have distributions of electrons in this manner. When the carbon forms a bond, the p and the s orbitals are mixed, and in this mixing, the number of orbitals are conserved. Here there are a total of 4 orbitals, and upon mixing you will get 4 sp3 hybridized orbitals. Now these orbitals, being hybridized, can form sigma bonds, and each of these orbitals can accept another electron from a bonding atom to complete the octet of carbon. Another way of mixing is to form a hybridized sp2 orbital. This sp2 orbital uses 1 orbital from the s and 2 orbitals from the p. A remaining p orbital is still present and untouched. The 4 electrons can be distributed along this sp2 and p orbitals. sp2 orbitals form the sigma bonds, so there will be 3 sigma bonds if you have a sp2 hybridized carbon, and there will be a p orbital that will form the pi bond. It is also possible to have sp hybridized carbon. In this case, 1 s orbital and 1 p orbital will mix to form 2 sp hybridized orbitals. The remaining 2 p orbitals will be untouched, and electrons will occupy all of these orbitals. The sp hybridized orbitals will form the sigma bonds, and the p orbitals will form the pi bonds. There will be 2 sigma bonds and 2 pi bonds in this case. If we are to examine an isolated nitrogen atom, it will have this arrangement of electrons, and once you mix them, you will get sp3 hybridized nitrogen atoms. There are 4 hybridized orbitals here, and one of the orbitals is already filled by 2 electrons. These 2 electrons will form the lone pair, and the remaining unpaired electrons here will form the sigma bond. So there will be 3 sigma bonds for the nitrogen atom. In the case of oxygen, upon mixing of the s and p orbitals, you will get 2 lone pairs for oxygen and 2 orbitals that are available for bonding. So oxygen will have 2 sigma bonds. Hybridization produces new directional orbitals that are more effective in forming sigma bonds. For example, when you form your sp3 hybridized orbitals, it can readily interact with s orbitals from hydrogen to form your new compound. Here, an sp2 hybridized orbital has directionality and can interact with another p orbital. This forms the strong sigma bond. Also, sp2 hybridized orbital can interact and form the bond with an s orbital. Hybridization influences the shapes of molecule according to the valence shell electron pair repulsion model. Acetic acid has an sp3 hybridized carbon. It has 4 sigma bonds, and this sp3 hybridized carbon, represented here by this black ball, has a tetrahedral arrangement. This carbon is sp2 hybridized. As you will see, it has 3 sigma bonds, and by 3 sigma bonds, it has a trigonal planar arrangement. Now for the case of this oxygen, the electron group geometry is tetrahedral, but since there are only 2 bonds, this will be bent. Hybridization describes the bonding molecules containing tetrahedral, trigonal planar, and digonal atoms. The remaining unhybridized p orbitals may form pi bonds. So here there will be an unhybridized p orbital from the sp2 hybridized carbon. It will form the pi bond to oxygen.